obtain the complete crystal structure, X-ray spectra are recorded for rotation around three mutually perpendicular planes of the crystal, okay, which provides comprehensive information on the various crystallographic planes of the lattice. Okay. The next the step which we have in analysis is to convert this data on the planes to knowledge of the positions of atoms in the unit cell which we have. Okay. So next, so this diffraction pattern can be used use to identify the crystalline phases and the structural characteristics we can use. So here we have like a by using this Debye-Scherz formula. So in the absence of homogeneous strains, the crystalline size, which is given by D is equals to K lambda by B cos theta, which we have. So next here. Lambda is nothing but already we know that is the what we call a wavelength which we have. So the wavelength of the X-rays, whichever we have. Lambda is the wavelength we have, and B is nothing but that is a full width half maximum we are going to be called. So full width half maximum height of a diffraction peak, and as already mentioned, theta is nothing but the diffraction angle we have, and here K is nothing but that is a Scherz constant, which is the order of a unity for a spherical crystal we have. So these nanoparticles often form what we call twin structures, and hence the Scherz formula may not be always gives true particle size. So this is what about the X-ray diffraction method, which we can be used to what we call get the information about the what we call crystalline nature of the nanoparticles. So by using this formula, we can get this the crystalline size. Yeah, by using the device. Right. So by using this device formula, we can get the what we call size of the crystalline DEV, which we have. And this it is also important to note that X-ray diffraction provides only the average crystalline size. So we cannot get exactly the size of the crystalline in the case of the nanoparticle, but here we have to remember that average crystalline size only we can get with the help of this X-ray diffraction. Okay. So due to lower energy of the X-ray beam, whichever we have used, so this X-ray diffraction intensities are low, particularly in case of low atomic materials, and hence detection of phases with small volume fractions is difficult with the help of this what we call XRD pattern, which we have. Okay, so that is what one drawback which we have in the case of this one. We won't get exact size of this crystalline line, but actually we'll get average size which we are going to get here. Okay. And next we'll move to this what we call a electron microscope. So what actually electron microscope which we have. Okay. So under the electron microscope, what we are going to get, we'll study about that here. Right. So this electron microscope, if you take, so this electron microscope is similar with optical microscopes only. So we can say that these electron microscopes, whichever we have, so these electron microscopes, they have a similarity. Some similarity is there. Electron microscope is having some similarity with the what we call optical microscope. With the optical microscope. So these electron microscopes have the similarity with the optical microscope. So in optical microscope, generally what we have is in optical microscopes, we use electromagnetic waves. We'll use EM waves there. EM waves, which we call it as electromagnetic waves. In optical microscopes, we'll use electromagnetic waves of appropriate wavelength scattered from the what we call specimen and are detected using a what we call a system of focusing lenses, which can be detected by using the system of focusing lenses we use. Okay, so that is what we have some similarity with the electron micro with the optical microscope. This electron microscope. So in the case of the optical microscope, the mainly we'll use electromagnetic waves will be used. So these electromagnetic waves of appropriate wavelength scattered from the specimen, which are detected by using this what we call focusing lenses. We are going to be get there in the case of the optical microscope. Now, if you coming to this electron microscope, if you take, so in this electron microscope, we won't use what we call electromagnetic waves. Instead of that, we are using here electrons are using. Okay, so these electrons are used in place of what we call electromagnetic radiation, which we use in the case of the optical microscope. So the electromagnetic radiation is replaced with electrons in the electron microscope. Okay. Otherwise, we can use here in the case of the electron microscopes, electrostatic or magnetic lenses are used instead of glass lenses. So in the case of this what we call optical microscope, we use the glass lenses, that is a focusing lenses, we use glass lenses. Whereas in the case of this electron microscope, instead of these glass lenses, we use magnetic lenses we are going to be used in this electron microscope. Okay. According to what we call this wave particle duality, so that is de Broglie wave particle duality nature. Electrons can sometimes behave as what we call particles. They can behave, and sometimes they can be behaves as a waves. Okay. So according to this wave particle nature, electrons sometimes can be behaves as a particles, and sometimes they behaves as a waves. Therefore, just like electromagnetic radiation, which we have used in the case of this optical microscope, so this electromagnetic radiation, which can be used to image the objects, uh, objects, that means which we want to be take image. Okay, so here, just like electromagnetic radiation, which can be used to image the object, electron waves electron waves can be used to image the objects here. So that means in the case of the optical microscope, generally we take this electromagnetic radiation which is used to image the object. Here, instead of that one, electrons will be used to image the objects here, right? Advantage of using electrons is that their wavelength can be tuned to a very small value. So what is the advantage which we have? Why we are by using these electrons in place of this electromagnetic radiation here? Uh, Electrons is that their wavelength can be tuned to a very small value. So that means the wavelength whichever we have, they can be tuned for a small value. That is the main advantage which we have by using these electrons here. So by how we are going to be tuned for a small value means just by changing their energies, by changing their energies so that the resolution can be increased. The resolution of the image can be increased. That means the image which we are going to be get, so we can vary the resolution. That means if we required higher resolution so that the image can be clearly seen. So if you want to see the higher resolution image, if you want to see, so just we have to vary what we call the size, that is the wavelength of these electrons we can be vary here. Okay. So if you see the wavelength of these generally which we have uh, of electrons, so this is what the wavelengths which we have. Okay. So by applying what we call different energies, we can get the different wavelengths here. So if you apply like a 20 kilovolts of energy, if you apply, so we will get the wavelength of the electron in the range of like a 0.0085 nanometers. Nanometer itself is a very smaller value. In that, again, we can get the wavelength of a 0.0085 nanometers wavelength we can get. And similarly, if you apply for 50 kilovolts of energy, then we can get like a 0.0053 nanometers you can get. Otherwise, if you apply like 80 kilovolts of energy, if you apply, so 0.0041 nanometers of wavelength of electrons you can get. And similarly, if you apply like 100 kilovolts, if you apply, you can get like a 0.0037 nanometers of wavelength you can get. So that is the advantage which we have in the case of the electron microscope. That means if you want to get the full clarity picture, so that we can increase the what we call resolution here. Okay, so we can increase the resolution. So how we can increase the resolution means by changing the what we call the wavelength. By changing the wavelength of the electrons, we can able to increase the resolution, so that the image quality which we are getting by using this electron microscope can be increased. Okay, so that is what advantage which we have in case of this electron microscope. By changing the wavelengths, we can get this uh, one. Okay, so now we'll move to here. Right. So generally, wavelength can be simply calculated by using what we call a de Broglie's relation, which we have. By using the de Broglie relation, we can calculate the wavelength. That is, lambda is equals to, we have h by mv. H by mv, where you know that h is nothing but the Planck's constant which we have, and m is nothing but the mass of the electron we have, and v is the velocity of the electron. So velocity can be found using what we call by using this half mv square formula, using e v is equals to half mv square here. Mv square. V is nothing but the applied voltage. This capital V is nothing but the applied voltage, and the small v is nothing but the velocity of the electron. So the wavelengths, whichever we have seen uh, whichever we have seen like a, right. So the wavelengths, whichever we have seen here, they looks like what we call very small, and one can have, otherwise one could have expected extremely high resolution. So as they are having very smaller wavelength, we can expect more high resoluted images we can expect here. So, but in general, the interaction between the electrons and the solid are quite complicated. The interaction of the electrons and with the solid, whichever means whichever the sample, whichever we have. So the interaction of these electrons with the sample are quite complicated due to what we call charge on incident electrons, due to the charge on incident electron. So, and subsequently interaction with electrons and ions in solids. Okay. So now we'll see this figure here. Right. So here, as we have seen in this figure, so here we have what we call interaction. This interaction results into backscattering. Okay. So as seen in this figure, so this interaction results into backscattering of electrons. So you see there are so many electrons which are backscattered. So backscattering of electrons. So here we have, so like this we have the backscattering of electrons can be seen in this figure here. Okay. So as the interaction results into the backscattering of electrons, so the production of you are going to get different electrons. So one is agar electrons you are going to get. Okay, one you are going to get it as a agar electrons you are getting, and as well as the what we call we are getting visible light also we are getting. Okay, so backscattered electrons we can get this production of agar electrons you are going to get, visible light you are going to get, and as well as the UV light you are going to get, and also even X-rays you are going to get, which we are calling it as a characteristic X-rays we are calling. So X-rays depending upon the energy of the incident electron. So type of sample and thickness of sample also it is depends. Means depending upon the sample, whichever you are going to take. Otherwise, the sample which we are using depends upon the thickness. So depending upon the thickness and as well as the type of the sample, so the production of all these agar electrons as well as this what we call UV light as well as the characteristic X-rays, otherwise the secondary X-rays you are going to get. Okay. So in any case, even what we call a parallel beam of electrons after interaction with the solid becomes defocused as illustrated in general. So a focused beam of electrons, a focused beam therefore forms a tear-shaped volume here. Okay, tear-shaped volume of beam interaction zone you are going to get here. Okay, so this is the top of the sample and this is the bottom of the sample we have. So there are, if you take this electron microscope, so there are two types of electron microscopes are there. One is, we call it as a, one is a scanning electron microscope we have. We call it as a SIM, we are going to be called. One is a scanning electron microscope is there. Another electron microscope which we have is a TEM, which we call it as a transmission electron microscope we are going to be called. So these are the two types of electron microscope. That means under the base is here electrons. So under these electron microscope, we have like two types, scanning electron microscope and as well as the transmission electron microscope we have. So this scanning electron microscope uses backscattered electrons from a sample for imaging and transmission here. Okay. So in the case of the scanning electron microscope, so mainly the image which we are going to be form in the case of the scanning electron microscope is due to the backscattered electrons. Is due to the backscattered electrons here. So by using this backscattered electrons, the images are formed in the case of the SEM here. Okay. And in the case of this, what we call transmission electron microscope, in the case of this transmission electron microscope, it utilizes the electrons transmitted through a sample. So the electrons which are transmitted through the sample, electrons transmitted through the sample, through the sample. So these transmitted electrons to the sample will be utilized and it is going to be give the image in the case of the transmission electron microscope. That is the reason why we call it as a transmission electron microscope. Whereas in the case of this scanning electron microscope, the backscattered electrons will be gives the image. Okay. So here to take this SEM, obviously the SEM can be used to image the surface of a thick sample. So this SEM can be used, this SIM can be used to image the surface of a thick sample. Okay. So if we have a thick sample, surface of a thick sample can be utilized in case of a SEM. Whereas in the case of the TEM, so this TEM needs have a thin sample. This TEM needs a thin sample. TEM needs a thin sample, whereas this SEM needs a thick sample. And in the case of this, what we call TEM, if you take, so as we said that it requires a thin sample is required, and this thin sample also, it should be have in the range of around 300 nanometers only. In the range of 300 nanometers only, it should have. The range of this thin sample should be in the range of 300 nanometers sample. So that high energy electrons can be transmit through the sample, because the main image which we are going to be formed with the help of TEM is transmission of the electron, so that we require a thin sample, so that these thin sample in which the electrons can be transmit to the sample. Okay. So this is what we required in the case of the TEM as well as in the case of the SEM here. So both these microscopes use electrons which need to reach the sample without getting scattered by air. That means the electrons, whichever we are going to be transmitted through a sample, otherwise backscattered electrons, whatever we have. So these electrons, whichever we passing through this without getting by what we call without getting any scattered in the air. Therefore, what we'll do is these electron microscope, whichever it may be having, SEM or TEM. So these electron microscopes needs vacuum for this operation. That means this SEM or TEM is operated in a vacuum. Means both will be kept in a vacuum. The need of vacuum is there in order to not get any scattering of what we call electrons by air. Okay. So this is about SEM, simply SEM about SIM as well as a TEM. So now we'll see in detail about what we call SEM as well as the TEM now. Right. The scanning electron microscope. Okay. So this scanning electron microscope, if you see as in the figure, so we have essential parts of the scanning electron microscope here. So these are the essential parts of the scanning electron microscope, which we have shown in this figure. So the scanning electron microscopes, electrons are emitted from a hard filament generally. So electrons are emitted from because electrons has to be passed through the sample. So here electron generation should be there. So these electrons, whichever we have, the electrons are emitted from a hard filament. Generally, these electrons are emitted from a hard filament. Through a hard filament, they are generated. Electrons are emitted from a hard filament usually. So, however, sometimes cold cathode. So, cold cathode means a cathode that emits electrons without heating it. So, sometimes we have a cold cathode also, which generate the electrons. So cold cathode we call. So cold cathode is nothing but a cathode that emits electrons without heating it. Okay. So sometimes we'll use this cold cathode also in order to generate electrons. So in general, hard filament is utilized in order to generate these electrons. Okay. So here a cold cathode which emits the electrons under the application of very high electric field. So how the generation of the electrons will takes place in case of the cold cathode is by utilizing what we call a high electric field. So this cold cathode emits the electrons. This cold cathode emits the electrons from the under the application of a very high electric field by a very high electric field. So if you use a very high electric field, then this cold cathode can be generate the electrons. So it is also known as a field emitter. This cold cathode, if you are using, we'll be calling it as a field emitter. We are going to be called. So if you use this cold cathode in order to generate the electrons, so such SEMs whichever we have, we'll be calling it as a FE SEM. We are going to be called. We'll be calling it as what? FE SEMs. We are going to be called. That is nothing but field emitting SEM we are going to be called. So in the case of this cold cathode, if we are using to get these what we call electrons, so we will be calling it as a FE SEMs we are going to be called. And these FE SEMs we will call and these are able to give better images than the hard filament. So if you take this FE SEM, so this FE SEM they'll be using, if you are using this FSM, they can be produce a good clarity of the image than the what we call if you use a the source as a hard filament if you use. Okay. So in general, so these FSMs are able to give the better images than this hard filament SEM, whichever we are going to be used. But however, this such FSMs is less common than what we call a hard cathode SEM. So mostly we'll use hard cathode only. Hard filament SEMs we are going to be used, but it's very less common to use this FE SEMs. Okay. So now if you take the scanning electron microscope, so in case of the scanning electron microscope, backscattered electrons, or we'll be calling it as a secondary electrons, will be calling. Okay, backscattered electrons are secondary electrons. So these are detected. Okay. So in some cases, it is also possible to use a sample current we are going to be used. Okay. So due to this interaction of a focused beam, so due to the interaction of this focused beam with solid, the backscattered electrons are somewhat defocused, resulting into lower resolution than one would expect. Means sometimes due to these backscattered electrons, sometimes the image resolution may be decreases here. Okay. So in an electron microscope, the electron beam can focus a very small spot size, using electrostatic or magnetic lenses. Okay, using electrostatic or magnetic lenses, we can get a very small spot size you are going to get. Okay, next, usually the electrostatic lenses. Okay, usually the electrostatic lenses are used here. Okay, electrostatic lenses are used in the case of what we call SEM. For a SEM, we will be using electrostatic lens. We are going to be used. Okay, so the fine beam is scanned or on the sample here. A fine beam of what we call scanned on the sample surface using a scan generator, and backscattered electrons are collected by an appropriate what we call detector. Okay, by detector we can collect the backscattered electrons. So signals from scan generator along with amplified signal from a from the electron collector generates the image of the sample surface. Okay. So signal from scan generator along with the amplified signal. So here we are using an amplifier. So amplifier signal from the electron collector generates the image of a sample surface. So in order to avoid the oxidation and the contamination of this filament, as well as reduce the collisions between the air molecules and electrons, so filament and sample have to be kept in a vacuum chamber. So as we have discussed that if any scattering will takes place due to the air, so all these what we call uh, mm, the filament and sample have to be placed in a vacuum chamber. Okay. So usually the vacuum which we are using means the vacuum whichever we are keeping in the vacuum chamber will be around 10 to the power of -2, 10 to the power of -3 pascals you are going to be have. The vacuum whichever we have created, the vacuum will be in the order of 10 to the power of -2 to 10 to the power of -3 pascals. or better is necessary for a normal operation of scanning electron microscope. Okay. So this makes electron microscopes. However, some manufacturers have been successful in marketing the electron microscopes known as which we call it as a environmental microscopes we are going to be called. So in which the samples can be at high pressure uh, around few hundreds of pascals, like 100 to 500 pascals we have. 100 to 500 pascals. Okay. So in the case of this scanning electron microscope, the sample whichever we are using, so the sample preparation is the should be minimized, and sample in biological conditions can be investigated in the case of this what we call SEM. Okay. So for this, the electrons are accelerated as usual in a high vacuum system, but they enter the sample chamber through a thin foil or aperture, we can say, so that a large pressure difference can be maintained here. Okay, large pressure difference can be maintained here. So one disadvantage which we have with the help of this what we call this electron microscope. So we have some disadvantage with this electron microscope, EM I am writing, electron microscope is that insulating samples cannot be analyzed directly as they get charged due to incident electrons and images become blurred. Okay, that is one disadvantage which we have. Okay, the disadvantage which we have of electron microscope is that insulating samples cannot be analyzed directly as they get charged due to incident electrons and images they may be blurred, means a good image you are not going to get. So therefore, if you use this, if you want to use this insulating samples, so these insulating solids are coated with a very thin metal film. Okay, thin metal film. They have to be coated with a thin metal film. They have to coat it. So generally, the metal which we use in order to coat that one is we'll use gold or platinum. Okay, gold or platinum we can be used. And the coating also will be very less. That is in the order of 10 nanometers, less than 10 nanometers you are having. So gold or platinum, making them conducting without altering any essential details of the sample. Okay. So the metal film is usually sputter coated on the sample to be investigated prior to the introduction into the electron microscope. Okay. So this enables even biological samples to be analyzed using an electron microscope. Okay. So additionally, some these microscopes provide with a low energy electrons flood gun to reduce the sample charging effect by providing more electrons to an insulating sample. Okay, that is what we have to remember here. So this electron microscope can also be used to obtain composition of sample using technique known as what we call energy dispersive analysis. We'll be calling EDAX, energy dispersive analysis of X-rays. We are going to be called EDAX. Okay. So here we have some image of this what we call SEM, right? So this is a scanning electron microscope image of ZNO with flower-like morphology. We have flower-like morphology and belt-like morphology here. Okay. So this is the image which we have. One of the what we call ZNO sample. Okay, scanning electron microscopy of ZNO with flower-like morphology and belt-like morphology. Okay. So here some method which we used, the chemical co-precipitation method is used in synthesis. Okay, chemical co-precipitation synthesis method has been used to obtain various morphologies by varying the synthesis parameters. Okay, so this is what about the SEM which we have. So the SEM image has been shown here. Okay, so next another type of spectroscope, another type of microscope under this electron microscope we have is a TEM microscope. Okay, TEM microscope, which we call it as a transmission electron microscope. We are going to call. So we are calling it as what? Transmission electron microscope we will be calling. So generally, the transmission electron microscope is ideal for investigating the nanomaterials as very high resolution is possible. Generally, what we call the resolution which we get by using this TEM is better than what we call around 0.5 nanometers. So in the range of that we are going to get. So by using this TEM, that is a transmission electron microscope, so we can use this TEM ideal for investigating the nanomaterials. Okay, it is ideal for investigating the nanomaterials, and they'll give as very high resolution as better than 0.5 nanometers using it. Okay, so as the name itself suggests that electrons are transmitted through the specimen in the microscope. So electrons of